happens by the photoelectric effect. You collect charge and you transfer charge in something called a potential well, and you detect the charge in some sensor and try and tell you a little bit about how this works. So I guess you're chemists, but I don't know still, let's assume. In silicon, which this is made of, you have conduction band and valence band, things are discrete energy bands. So you have a structure like this in energy, this is energy, you have all electrons filled in the valence band, you have around an electron volt of gap, and then you have empty states over here. What happens when you shine light? Due to the photoelectric effect, the electrons which are in the valence band can be sort of excited up into the conduction band by a colloquium of a photon, giving you an electron and a hole. So your charge is now in a semiconductor. The next thing, in a semiconductor, the simplest semiconductor device is a p-n junction. You have n-type semiconductor, p-type semiconductor, you must have heard this sometime. When you combine them together, what happens? One of them has more holes, one of them has more electrons. Because of that, charge carriers separated, you get an electric field, and there is a voltage that develops. And I just turned that around. This is n-type, this is p-type. There is a field which the potential which peaks at the junction. So if you take a snap like this is the electric field potential which peaks over here. Now there are 3 electrodes arranged like this. What happens if I put a voltage on the middle one? So if I put a voltage on the middle one, I'm sort of pushing that curve up. So I have additionally applied an external voltage, and that external voltage, what it does is locally over here, it has pushed this potential up. Okay? This is how you can make your little pixel or little device where you collect your charge. Because now anything over here will try and electrons, just imagine that electrons will like get trapped in these potentials, you can do it. So what you do, suppose you have an array like this, you have n-type and p-type, and you have these groups of 3 electrodes, and photons are coming in. As photons coming in, you generate electrons, and these electrons sort of get collected in the center of these electrodes. Okay? Now they are collected, just like we collected our rain in our buckets, we need to push these things and read them out. And this is where the idea of having 3 electrodes per pixel is going to help you. And just like we did for the well, for the conveyor belt, we're going to somehow shift the electrons from one well to the other well. And remember that sketch you saw in the original drawing from the notebook? This is kind of the sketch. The sketch just tells you, if these are electrodes, what voltages do I apply on them? And generally in digital circuits you apply 0 volts and 5 volts. So these are just a sequence of, at various times, I need to apply different voltages. So suppose the voltage, the 5 volts is now applied to those 2 things which you see in red, that's where the charge is collected. Because wherever you apply the voltage, that is where your potential well is. What you do, in the next time slide, you apply the 5 volts to the neighboring one on the right as well. So this just spreads out the region where the charge is located, just spreads out this charge. In the next slide, you switch off the earlier one. You switch the one to the left off. Now what has happened, because the potential is centered around the middle electrode, the charge collects below that. So you shifted the charge a little bit. You keep doing this. You put the potential on the next electrode to the right. The charge spreads out a little bit, shut it off, the charge moves this way. So by this technique, you can actually move the charge. So if I do this in sequence, what basically happens is the charge just travels from left to right, and you can read it. So this is the equivalent of your bucket bringing per electron. Now the idea that the original CCD was to have an entire area. Your pixels are here. You can transfer them this way and read it out in the last line. This is exactly similar to the conveyor belt picture that I showed you. This is nice, it works. Many of the early CCDs are this way. The issue is you have to wait. I can't take my next image until I have read out all those things. So this is solved by this concept. And the next thing, the concept idea is have something called a frame transfer CCD. Silicon is relatively easy. Right? So at the expense of having a larger chip, what they do, they have a chip where only half of it is used for the image, half of it is used as a temporary register. So what you do, you store your image, so different intensities, and then you just transfer the image into this set. And while you are reading out this set, you can still use this part to integrate the intensity of the next image that you want to take. So this is key to making a practical device. It really allows you to use time more efficiently. You use half of your area for storage, half of your area for the imaging. There are other variations on that theme that I can use. You ask me how will you make color CCDs. It's actually very simple. If it's a very low-end device, cell phone camera or something like this, they just have filters. You have a mask on top of your CCD array, and instead of having one pixel, now you use 4 pixels. They have 2 greens, 1 blue, 1 red. You need to do that because your eye sensitivity is much more in the green. And then you can combine the information of the red, blue, and green. More sophisticated devices, you see a high-end camera, it is a 3 CCD camera. That's because what they use is a prism. They use a special prism which splits up red, blue, and green into 3 things, and they use 3 independent CCDs to gather that information. So this is the color CCD. Okay. And today, if I look at what is the state of the art of CCDs, they are rather amazing devices. They have over 90% quantum efficiency. Of all the photons coming in, 90% of them give you some electrons at the end of it. Compare that with film, which is 5%. Right? You can, because of the low dark currents and noise and all you can design it for, you can actually have long integration time before everything gets completely washed out. And you can actually have a huge intensity contrast because of the number of electrons you can accumulate for every pixel. While a lot of this initial things happened in Bell Labs, CCDs wouldn't reach every cell phone and every digital camera. There's a lot of consumer cheap CCD work was done by companies in Japan, notably Sony. Sony has done a lot of work on making these cheap, mass-produced CCDs available. CCDs are used everywhere. This is a close-up of a simple CCD. You can actually see the red, blue, green, the mask. Right? It's taken from a 2 megapixel camera. You get very large CCDs or arrays of CCDs. This is something from a telescope. Astronomers are the most critical people for requiring high-end CCDs. This is for digital surveys of the sky. Right? And if I look at the state of the art today, it's something like this. You know how many megapixels you have? This is a single CCD, not an array of CCDs. This is a single CCD, 4-inch in size, more than 10,000 by 10,000. This is more than 100 megapixels in a single CCD. So still your cameras are typically at 10 megapixel, 12 megapixel. Already the state of the art in CCD is more than 100 megapixels. This is amazingly difficult to make. I mean, most semiconductor chips are not very big, right? So and you need a very, the yield in this, you cannot afford to have a single defect in your wafer across a 4-inch area. It's almost unbelievable. I don't know what the yields for these processes are, but I don't think they'll be very high. So, but this is what the state of the art is. Okay? One people who are very happy with CCD scientists are astronomers. You must have heard of Moore's law for computers, the speed of computers and the number of chips on a computer, things like this. So Moore's law, things keep doubling every so many months. The yellow dots are the number of transistors in a CPU. Since 1960s, this is a log scale again, they have been going up steadily. Right? Similarly, CCDs, if you look at the number of CCDs, the number of pixels you get in a CCD, you must have noticed this, right? A few years back it was a 1 megapixel thing and now you have 3 megapixels and 10 megapixels. CCDs are also going on a very similar logarithmic behavior with time. It's like a Moore's law for them. And similarly, if you look at the number of galaxies that we discover per year, is also increasing in a logarithmic scale like this, thanks to the CCD being used. Okay? Even for scientists, the CCDs are very important. In fact, most sensors, X-ray sensors, everything is today tending towards being a CCD. So, I will stop here, summarize what I said. The masters of light, 2 important concepts, key concepts that have revolutionized what we know about how we communicate and how we image over the last 40 years. Charles Kao, a very critical idea that your loss is not due to the glass itself, it is due to impurities in the glass. If you can reduce the impurities in the glass, you will bring it down. You can actually bring it down to 20 dB per kilometer, is what he predicted when it was 1000, and today it's actually something like 0.1. So long distance communication through fibers, thanks to Charles Kao. Right? Boyle and came up with this concept, how can I store packets of charge and move them around carefully and manipulate them in order to read out a pixel of arrays, never used for memory, but finds it smart as an imaging sensor. 2 things without which the world today will be very difficult. Thank you. We have to next.
Let us thank arnab, Bhattacharya